Let us next see number 26. In this one we have to find the fourth derivative of the function y, and there are two functions given. The first one is minus 2 sin x and the second one is 9 cos x. So let's see the solution. Okay, so we start the solution with part A first, of course. And we are just going to remember that the derivative of sin x is cos x and the derivative of cos x is minus sin x. So if we differentiate this once, one time, then it will be minus 2 times the derivative of sin x. Why? Because you are using the constant multiple rule, and the derivative of sin x is cos x. So the first derivative is minus 2 cos x, and the second derivative will be obtained by differentiating this one once more. So again minus 2 remains outside, but when you differentiate cos x you get minus sin x. So minus 2 times minus sin x is 2 sin x. Then the third derivative would be obtained by differentiating this once more. So 2 remains outside and the derivative of sin x is cos x. And finally the fourth derivative is obtained by differentiating this once. So 2 is 2 and derivative of cos x is minus sin x. So that's how we get minus 2 sin x. For part B, again same. This time the function is 9 cos x, because we are starting with cosine, so immediately we are going to get minus. So the first derivative is minus 9 sin x. Then you differentiate once more, and differentiating sin x you will get cos x. So the next one is minus 9 cos x. Then you differentiate once more to get the third derivative. Differentiating cos x will give you minus sin x. Multiply that with minus 9, you will get 9 sin x. And finally the fourth derivative is obtained by differentiating this one once more. So 9 remains outside and sin x gets turned into cos x when you differentiate this. So that's how we have this solution. Next we have some problems on limits. We have to calculate this limit, say in 28. So this is the limit as x approaches minus pi divided by 6 of this function. Now it looks quite complicated, it is complicated, but the fact is that this is a continuous function at this point. So the limit can be obtained simply by replacing x with minus pi divided by 6. How is this a continuous, how is this a continuous function? Well, we already know that the cosecant function, what is cosecant function? 1 divided by sin x. Cosecant x is 1 divided by sin x. And because sin x is continuous, so the reciprocal of sin x is also continuous at those points where sin x does not vanish. That means at every real number except the integer multiples of pi. This is not an integer multiple of pi. That is why cosecant function at this point is continuous. Multiply that by any constant, here by pi, still it's a continuous function. Cosine function is continuous at every point on the real line. So in particular, cosine function would be continuous at this point if you put x equal to minus pi divided by 6. But why? That is because this is a composition of two functions. And we know that when we compose two continuous functions, the composition is also continuous. Add 1 to that, which is a constant, this remains continuous, and the square root of this is also continuous. That is because we will see when we put this point here, finally the real number that we are getting under the radical sign will be a positive real number. At any positive real number, the square root function is continuous. So all in all, what we now have to do is we just have to put x equal to minus pi over 6. That's all, that will give us the limit. Okay, so accordingly in the solution we do just that. We straight away replace x with minus pi over 6. Now cosecant function is an odd function because it's the reciprocal of sine and sine is odd. So this minus sign goes outside cosec function. So that way we get minus pi times cosec pi over 6. Now cosec pi over 6 is 2 because sine pi over 6 is 1 divided by 2 and cosec is the reciprocal of sine. And that is how we get minus 2 pi here. Now unlike cosec, which is an odd function, cosine function is an even function. We know this. And that is why cos minus 2 pi is equal to cos 2 pi. And cos 2 pi is 1. So that's how we have 1 here and the answer is root 2. Now you may find it a fun little exercise to do this. You type this on the Chrome browser. Desmos graphing calculator. And there you graph this function. Okay, you will see that on the left side there is a place where you can put the equation of the function. What you do, you write y equals square root, you will understand, all the comments are there, square root of this, and instantly the graph will appear on the right side. And then you locate this point. How will you locate this point? Along with this graph, y equal to this thing, just below that there are other places also. There you also draw this line. A vertical line will appear where this minus pi over 6 is located. And then with these two graphs, you also draw the graph of y equal to square root of 2. And see if the graph of this function is really approaching square root of 2, which will be a horizontal line, when your x is approaching the vertical line. You will see that this really happens. Okay, so I want you to go through this. Let us next see another one. So next let us consider 30. And in this limit also, again we can put x equal to 0 and find the value of the limit. That is because this function is continuous at x equal to 0. Using the algebra of continuous functions, you can conclude that this function is continuous at x equal to 0. You just have to proceed like the previous one. Tan x is continuous at every real number other than odd integer multiples of pi divided by 2. 0 is not an odd integer multiple of pi over 2. Secant x is also continuous precisely at those points, any real number other than odd integer multiples of pi over 2. And that is because these are the points that we are avoiding. At these points, cosine becomes 0 and tangent is sine divided by cosine and secant is 1 divided by cosine. But our 0 is not a problematic point. So tan x is continuous there. You add pi to it, which is a constant function and hence is also continuous. It's continuous everywhere. So the sum is continuous at 0. Alright. Similarly, if you multiply secant x by minus 2, multiplying a continuous function by a constant again gives us a continuous function. And tan x already is continuous. And this difference then is, difference means because I multiplied by minus 2, so we have to consider sum. Sum of tan x and minus 2 secant x is also continuous because the sum of two continuous functions is continuous. And finally, the quotient of these two continuous functions is going to be continuous at those points where the denominator does not vanish. Does the denominator vanish if you put x equal to 0? Or more accurately, this is what I should ask. Is the limit of the denominator 0 as x approaches 0? Because the denominator is continuous, that limit is obtained by simply putting x equal to 0. If you put x equal to 0 here, tangent vanishes. Secant 0 is 1, so that means the denominator or the limit is minus 2. No, it is not 0. And that is why the quotient is also continuous at x equal to 0. And because of all these things, you can just simply substitute x equal to 0 to calculate this limit. If you want, you can write all these things as the justification for doing this. I am not going to write them here, however, we are straight away going to do the calculation. So this is the solution. Now it's just a simple matter. You write 0 in place of x and you get the answer as minus pi divided by 2. Next, let us consider 32, and here we have to calculate this limit. Limit of cosine of pi theta divided by sin theta as theta approaches 0. We start the solution with this limit. Let us first see what happens to pi theta divided by sin theta as theta approaches 0. So, pi of course immediately comes outside because it's a constant, and then you can write theta divided by sin theta like this, the reciprocal of sin theta divided by theta. Now you know that the limit of this is 1, which is non-zero. So the limit of its reciprocal would be the reciprocal of 1, which is also 1. So that's how we find that this limit is pi. Or in other words, if you write a single variable in place of this function, okay, and say that is t, then t is approaching pi, or the limit of t is pi as theta is approaching 0. So now we can use this information to finally say what this limit is. So we can write this limit in terms of this new variable t. As theta tends to 0, t tends to pi. And this is what you are calling t. So that is why you can write cos t here. And then next, in place of this limit, we write cos pi. Why? Because cosine function is continuous at every real number actually. So in particular at pi also. That is why the limit of cos t as t approaches pi is equal to cos pi, because that is what continuity is, and cos pi is minus 1. So that's how finally the answer is minus 1. Next, let us consider 34. In this one, we have to find the limit of sine of kt divided by t as t approaches 0. And it's mentioned that k here is a constant. K is not changing as t is changing. So let's see the solution. We divide the solution into two cases depending on whether k is 0 or not. Let us first consider the easier one. If k is 0, then the function itself becomes 0, because you are having sine 0 divided by t, so this is 0, and the limit of the constant function 0 of course is 0, and that is actually just k. Next we go for the case where k is non-zero. If k is non-zero, then we change this sine kt divided by t into this. We multiply and divide by k, and we can do so because k is non-zero. So that way we get kt here and kt here as well, and because k is constant, it goes outside, okay, by the constant multiple rule for limits. and then we are left with sin kt divided by kt, and you know that this limit is 1. Actually, this doesn't immediately become 1. There is an intermediate step which we normally do not write, and that step is this. As t approaches 0, kt also approaches 0, and that is why sin of kt divided by kt approaches 1, because kt is approaching 0, and that's how you have 1. But anyway, it is 1, and so here also ultimately we are getting k. So the answer in general is k, but the solution goes through two slightly different cases. So the final answer is actually k, even when k is 0. And the next one say we consider the 40th one. Here we have to find the limit of 6x square times cot x times cosecant of 2x as x approaches 0. So the function is a little long, it has many ingredients. And I forgot to tell you something about this part of the previous solution. See, whenever you are differentiating or whenever you are calculating limit, because of the constant multiple rules for both differentiation and limit, there is a tendency, a habit forms of taking the constant outside. So you may end up taking k outside from sin itself and outside this sign and outside the limit at once. Don't do that, okay? Sin of kt is not equal to k times sin of t in general. Instead, and that is why we had to divide and multiply by k, so that we can create the same thing here in the numerator as well as in the denominator. Although you note one more thing, that if you do so, if you take k outside and write limit of sin t divided by t as t approaches 0, and then you see that that limit would be 1, ultimately you are getting k, but the process is wrong. Okay, so you won't really get, you should not get any mark for that. But anyway, let's go for the solution to the 40th one next. So for this solution, we write these different things, we rearrange its different parts. For example, in place of 6x square, we write 3x and 2x. We split cot x. Split means we write what cot x is, cos x divided by sin x. And cosecant of 2x is 1 divided by sin 2x, and then the limit gets distributed over these individual parts. So that's how we get limit of cos x times this 3 of course comes outside because it's constant, times limit of x divided by sin x times limit of 2x divided by sin 2x. Don't take this 2 outside because here we need it. This limit is cos 0 because cos is continuous at every real number, in particular at 0, and cos 0 is 1, times 3 times this limit is also 1 and this limit is also 1. So that is how the answer is 3. Let's see another one. Number 46. Limit of sin 5x divided by sin 4x as x approaches 0. Originally in the function we do not have any x. We have x here, but outside the sin functions we do not have any x. So that means we have to create x, and that too a little smartly, not just simply multiplying and dividing by x. So we do this. 5 divided by 4 times 4x divided by 5x times this. And then you can see that 5 over 4 will go outside, and you can rewrite this part like this. Sin 5x divided by 5x divided by sin 4x divided by 4x. And then you know that the limit of this ratio is 1. and the limit of this ratio is also 1 as x approaches 0, because the denominator limit is not equal to 0. So, the limit of the quotient is the quotient of the limits, that is 1 divided by 1, which is 1, and that is why the final answer is 5 divided by 4.